Dear students, in this presentation, we will see the next topic, that is threaded binary trees. Let us take one example of binary tree. This is binary tree because any of the node, it can be root node or it can be a parent node, the number of children does not exist, is not more than 2. The degree of any node is not more than 2. It can be 0 or it can be 1 or it can be 2. That is why this tree is a binary tree. For example, in this tree, A is the root node. A has got 2 children, B and C. B children are D and D. D children are H and I. C children are F and G. The same tree can be represented in the linked list form. This is a linked list representation of the tree. A is a data node having left child B, B left child is D, D left child is H, D right child is I, B right child is E, and A's right child C, C left child is F, C right child is G. So after construction of this binary tree, you can observe that there are too many null nodes. So the main intention of threaded binary tree is to nullify or reduce these null nodes. As you can see in this diagram, there will be 2 null nodes for each of the leaf. H, I, E, F and G are the leaf node. There are 5 leaf nodes. 5 into 2, 10 null nodes exist in this tree. For construction of threaded binary tree, we should know the in-order traversal of the tree. The in-order traversal means first you have to visit the left child, then that root, then to the right. So if I start from A has got left child, I have to go further. B has got left child, I have to go to the next level. D has got left child, I have to go to the next level. So here this node is not having left child, so this is ultimate left of D. So that is why the first node is H. Then after visiting the left node, after visiting the left of T, then that root itself, then to its, that means you have completed the left of B. Then you have to visit B. After visiting that root, you have to go to the right side. Here we have got only one node, so after B it is E. With this we have completed all the nodes of left of A, then that root itself, the parent itself, A. Then you have to take the right side of that. In that right side, we have got one left child, F, then that node itself, then the right. So in order traversal of this is H, D, I, B, E, A, F, C and G. This is the first step, writing the in order traversal. The rule is that if left child is null, as you can see here, if left child is null, then what to do? If left child is null, you have to replace that by a pointer which points to the node that would be visited before. That means in order predecessor. Okay, so you when you are getting that left node is null, you have to connect that link to the predecessor. If right link is null, you connect to the successor. If right child is null, you replace that with the right child with a pointer to the node that would be visited after, that means successor. before predecessor after successor. So this is the thing we'll see here. Here for H you have got one null node, left null, right null. For I also left, right. For E left and right. For F left and right. For G also left and right null. Now we'll connect it. For H, it is not having any the predecessor node. As you can see, there is no node at all. H is the leftmost. For the time being, keep as it is. For the time being, just draw a line. Just draw a line like this. This is the thing. H right side is also null. H right link is also null. Now what to do? You have to connect this to the successor. H successor is D. You have to connect that to the D. Similarly, for I, left node, in order predecessor. For I, D is the in order predecessor. So connect that to D. I right side, in order successor. So in order successor for I is B. You have to connect these to its successor. For E left link is null. You have to connect to in order predecessor. The node which is before E is B, so you have to connect it. As it is a leaf node, right link of the T is also null. You have to connect to the in order successor. Here you can see in order successor of E is B. You have to connect it here. Then F is a leaf node. It has got right link null and left link is null. If the left link is null, you have to connect it to the predecessor. For F, previous node is A. You have to connect it like this. As it is a right child, as it is a child node, external node, leaf node, right link is null. You have to connect to the successor. F successor is C. You have to connect it here. G is also leaf node, left to its predecessor. For G, C is the predecessor. So you have to connect it like this. Right side, you have to connect to the successor. But here, there is no node at all because it's ultimate right node. With this adjustment for the T, we have reduced that null pointers. Earlier it was around 10 null pointer. Now we have reduced to 2. That many number of null pointers are now reduced. Why the null is dangerous? Suppose you are unable to store the proper address or the null address, it will be it will give the problem. So here, after reducing this, we have got now two dangling pointer. We call this as a dangling pointer because it is not pointing to any of the parent. In the next phase, for this purpose, you have to take one header node. To remove that dangling pointer, you have to have one header node. Actually, we don't have any data to keep, but you create one head node. Now, after that, this left of that edge should point to that header. Also, the ultimate right should also point to the header node. This is the adjustment required. After creating this node, the null point is now reduced to 0. So this is the final version of threaded binary tree. Now how to do this programmatically? Compared to the earlier version of the structure, now we have got one more link. That link is not the direct link, it is the threaded link. Now we have to differentiate. As you can see in this diagram, this is a link from parent to the child. This is a link to the higher level. These dotted lines are the link to the upper level. Now we have to differentiate the link from the parent to the child node and link from the child node to the parent node. For that, we have to add two fields. We can indicate that with the bit, short number you can take, just to indicate that whether it's a normal link from parent to the child or threaded link from child to the parent. So here we have got two link. It can be in the left side or it can be in the right side. For that purpose, short int left thread, short int right thread, these two are added in addition to the old. Old you have got left link and the right link and the data node. This is adjustment. Now what value you have to put? Suppose that link is a threaded link, put value 0. If that link is the normal link, put value 1. Like in this case, this is the normal link. I will be taking the example of node D. Node D. Data is D. D left child should point to E. So this will go to H or H address is stored here. Here the address of I should be stored. Address of I. This is for H. Now to tell this as the normal link from parent to child, here you have to put 1. This indicates that this link is the normal link from parent to the child. Similarly, here also you have to put right link, right thread link value 1 because it is the link from parent to the child. Now I will be showing the values for the node H. The data node is H. H has got two links, right link and the left link, but link here it is a thread. Here you have to put the value 0. Right is pointed to D. Here address of D is stored. Address of D is stored here. Then here address of that header node is stored. To indicate that is a threaded node, a threaded link, put value 0. So this will solve the dangling pointer problem. So threaded tree are the special type of tree where null nodes are nullified. There will not be no null node. To differentiate the normal link and the threaded link, we have to add two fields. One is for the left and right. The value can be 0 or 1. 0 will indicate that that link is a threaded node. 1 indicates that it is a normal. That's all about threaded binary tree. Thank you.